Okay. So today we're going to talk about saturation, underexposure, bit depth, and image display. So now we're sort of moving away a little bit from the hardware, even though we'll come back a bit later today. And then, or we're going into the software really of your microscope. So saturation and underexposure. We have this in this image that we have. So all this is done with the NIS-Element, the Nikon NIS-Element, but the same thing exactly applied to your microscope. In this image that we have 3 channels, 1, 2, and 3, and this is the overlay. And at first glance like this, it may look like the channel 1 and channel 3 are very dim, and they are not acquired correctly, whereas channel 5 is okay. However, that's not the case. So if we push the saturation mask, what we can see is that channel 2, this channel, is actually saturated, and the others are not. So if we look, and you can do the same thing in your software. So if we put our mouse somewhere in the image, we're going to see 2 things: the XY coordinate of the mouse within the image, and then we have 3 different numbers, and each of them corresponds to the intensity in each of the channels. So we have this channel is 441 at this point of the image. This one is 385, and this one is 4095. And that's a bit of a magic number. So 4095, what is the problem with that? These pixels are saturated. So what does saturation look like if we look a little bit more in details? So this is what it looks like if we go a bit closer, and all these pixels that are color-coded in red have the intensity 4095. They all have the same intensity, whereas it's extremely unlikely, or pretty much impossible, that in reality all these pixels have the same intensity or the same amount of flow force everywhere. So clearly you would have the same thing as here. The intensity would change everywhere. So when we remove the color mask, what we can see is that these areas are like solid white. There is no details at all in these areas. This is what it looks like without the saturation mask. This is an artifact of microscopy, and all the pixels that are color-coded in red are saturated. So what does it look like if we look a little bit closer? This is a fluorescent bead, and it is here well exposed. What we can see when it's well exposed is that we have some sort of structure on the bead. Even though it's just one bead with fluorophore, there's some sort of structure. This is because our microscope and our objectives can really resolve really nice and fine details. So we see the little structure. And if we do a histogram where we plot like an intensity profile, where we draw a line like this, and we can see the intensities along the line, what we can see is at the top here, where the line is across the beads, we have all sorts of intensity going up and down. Whereas if we saturate the bead, this is what it looks like, and what happens is the top is flat. There is no details at all recorded in these areas. So all the red pixels have the maximum possible intensity. It's not possible for the sensor to record higher intensities than that. So the intensity information recorded for these for the saturated pixels is incorrect. Okay, it is absolutely incorrect. So there is no details at all, and what we need to do to correct for this is, for example, change the exposure time, expose less. If we have a camera-based system, we can lower the gain, we can lower the illumination power, etc. But we need to put less light on this. And we need to be very aware when we do Z-stacks or during time lapses, because then the intensity can change over time. And during a Z-stack, the intensity can change a lot over the Z. And therefore, we need to be very conservative when we set the gain, the exposure time, and the illumination power. It's not only what we see in one plane or at one time point is going to change clearly. So what about underexposure now? What does it look like? So this is an image that is underexposed. what you can see is that the background, when we use the color mask for saturation and underexposure, the background is solid blue. And if we look a little bit with our mouse in the intensity there, we see that all these pixels that are color-coded in blue have the same intensity, 0. So if we remove the color mask, it's very difficult to see. So with a trained eye, you will be able to identify saturation without the saturation mask. But underexposure, it's pretty much impossible to see it because we're so used to having a black background anyway. So this is an artifact of microscopy. And again, the blue pixels are underexposed. And yes, it's a very nice background, but there is absolutely no details at the edges of the cells. And I will show you this later. And it's much easier to detect saturation than underexposure. Unfortunately, if you send an image like this in an article and the journal does their job properly, this image is likely to be rejected. So how painful would that be if your paper is rejected or is questioned simply because you put the wrong offset when you detected this image? So please do your work properly. Never any saturation and never any underexposure either. So where does that come from? Saturation and underexposure come from the dynamic range and the bit depth, so I will talk about that. And how to detect them, so we will talk about lookup tables and histograms. And then what are the consequences of saturation and underexposure? So there is no usable information, and I will show this a little bit. And then how can we change the display? How can we adjust the display when we need to use the images? Well, we'll talk about brightness, contrast, and gamma. So let's talk about the first point, where the saturation comes from and underexposure come from. So they come from the bit depth and the dynamic range. So what is this? In this image, and you will see the same thing, so you actually need to show me in your software, this is one of the assignments for this weekend, you have to show me in your software where you can see the bit depth and what the different bit depth options are on your software. So this is the bit depth, and it says 3 times 12 bits, and it's 3 times because we have 3 images. So each of these images is acquired in 12 bits. So let's go back to understand this. Let's go back to this image that I've shown you before. What is a good sensor? I said we have some electrons. The sensor detects only some of the electrons, so this is related to the quantum efficiency of the sensor. And then the photons are, 3 photons, we get 1 photon, and the photon triggers a charge, so we get 1 electron for each photon that is detected. Then we amplify the signal. And then we have a voltage, current, basically. We read the current, and then this is converted into a digital signal with which we build the image, digital image. So this is true for all cameras and detectors. And what happens with bit depth and dynamic range is here at this last level, where we're going to read the voltage and convert it to a digital signal. So the dynamic range is a property of the analog to digital converter, this last little machine that we use before we make the image. Whereas the bit depth is a property of the image. So we'll see why that matters. The dynamic range of the sensor, so this is a property of the sensor, which means that it comes with your sensor. The only way to change the dynamic range, so there's a few parameters that will influence the dynamic range, but you cannot change the dynamic range directly. So this is a property of the sensor. And what is it? It is the ratio between the highest to the lowest signal, actually in electrons, that your sensor can detect, okay? So it's a ratio. It's the ability of the sensor to read dark areas with intensity details and at the same time bright areas without saturation. So it's a specification of the sensor. You cannot choose directly in the software the dynamic range, but it depends on the bit depth and the readout rate. So somehow we can reduce it. So we will see what it is. But it cannot be changed after acquisition. So you can see the bit depth as something like a well. And if you have a very deep well, you can put a lot of water in your well. But sometimes you may have conditions where you can fill up only half of the well. And this is what happens in certain conditions of bit depth and readout. We can only fill half of the well. But it's anyway an advantage to have a big well, because if you need the big well and a lot of water, then you can you can get a lot of water. So that's a little bit the dynamic range. On camera-based systems, we have a very high quantum efficiency. You remember some cameras have a 95% quantum efficiency at some place in the spectrum, and that means that 95% of the photons that reach the sensor trigger an electron. So it's a very, very high compared to what we have on detector-based system like spinning disk confocal, where the highest of the highest you can get is 45% of the photons are actually triggering an electron. So on camera-based system, we have basically a very high quantum efficiency, and the exposure time is in milliseconds. And during these milliseconds, we have all the pixels are exposed to the light, right? So it means that each pixel is exposed for milliseconds. So this is very short as far as taking an image with millions of pixels is concerned, but for each pixel is actually much, much, much longer than the time that each pixel on the point confocal is exposed to. So we have exposure times in milliseconds, and the electrons are accumulated in the well before the chip is emptied. So there is an accumulation, and therefore camera require a high dynamic range because they need to have a big well to get a big bucket so that they get lots of photons, like drops of water. So the cameras require a high dynamic range. For a detector-based system like single point confocals, we have in general a low quantum efficiency, about half in the best case. Quantum efficiency means like more than half of the photons that actually make it to the sensor are not detected, unfortunately. But the pixel dwell time, the time where the scanner stays on each spot in the sample. So this is the time where each pixel, if you want to say, is going to be exposed to light. This is in microseconds, so it's one order of magnitude less than. So it's much, much, much lower. So very quick pixel dwell time for each pixel. And the electrons are not accumulated, they are just read on the fly. So detectors usually work well with a low dynamic range. And we will see that there is a difference. For those who image on the point confocal or on the camera-based system, there will be a difference in what you are selecting on your software. So what about the bit depth then? The bit depth is the bit depth of the image, and that is something we can choose. So it is the number of intensity steps between the dimmest and the brightest possible intensities in the image, okay? So the dimmest is going to be black and the brightest is going to be white, completely white, and in between we have lots of grays. And how many grays do we have? This is the bit depth, basically. And that can be chosen in the software. We will see when we want to choose one bit depth or not. And this is the case for both detectors and camera systems. And it can be changed after acquisition as well. And the images that you need to compare, they must be acquired at the same bit depth. Otherwise, you just cannot compare at all the intensities. The numbers will be very different. So what does that mean, bit depth? If we have an 8-bit image, we have 2 to the power of 8, which means 256 gray levels like this between completely black and completely white. So completely black is going to be 0, and then completely white is going to be 255, and therefore altogether we have 256 levels of gray. And anything in between here is going to have an intensity value, which is an integer between 0 and 255. If instead we're acquiring an image in 16-bit, we have 2 to the power of 16 levels of gray, and that is 65,536, so that's a lot. And what you can see in here is we also have the first level is 0, and the highest level, which is completely white, is 65,565. And in between, you can see we have so many levels of gray that it looks really like a gradient, this very smooth gradient. And so the same thing happens in our images. If we have only 255 levels of gray, we're going to have gradation in the intensity level. Whereas if we have a high bit depth, we're going to get very smooth gradation from one intensity to a little bit brighter, for example. Computer screens can only display 8-bit, so 256 levels, and human eyes are crap. So I say, do not believe your eyes. I mean that anything is better than your eyes. So 100 level of gray maximum, this corresponds to about 7 bits. So you should not believe your eyes. You should always explore things with your mouse or with a region of interest and look at the numbers and not believing your eyes. So what are the advantages of high bit depth? So this is the little summary of what we have when we have different bit depths. In general, you're going to have 8, 12, and 16, but some cameras can have 11 or 14 as well. So here is the calculation that we have, and you can recognize maybe in our first image, all the red pixels were 4095, which is the highest level of this bit range, because we have the 0 as well. So the minimum is 0 and the maximum is 4095. And so all these pixels, if all the pixels in the image that have the highest bit depth intensity are considered saturated, it means they could be higher and the detector is not going to be able to tell you if it's higher. So these images that are required in these bit depths, the 8-bit images can be read by any software that reads images, whereas all the images that have a higher bit depth require special software. When we have a high bit depth, we have a lower risk for saturation, because when we use a high bit depth, we're using the whole dynamic range of our detector. So we're able to detect all the way from the minimum that the detector can do all the way to the maximum. And so we have a lower risk for saturation because we have lots of different bit depths. And also we have fine intensity details in both the bright and the dim area. So a little bit more gray, a little bit less gray, very fine details when we use a high bit depth. It is much better if you want to do the edges, let's say, are much finer, detailed and defined. They are defined much better, the edges. And also, so it helps if you want to segment crowded objects. You have to have fine details in the edges during image analysis. So the file size for high bit depth, so everything above 8 is considered a high bit depth, so 11, 12, 14, 16. These files all have the same size, okay, because this is the way computer works. They work with either 8 bits or 16 bits. So even if your image is less than 16 bit, the computer will fill in and you will get the same size as 16 bits. And then what are the applications of imaging with a high bit depth? Well, if we have a sample that is very dim in some areas and very bright in others, and we want to get a fine readout of both of them, and we do not want to have saturation, so then it's good to have a high bit depth so that you can display both the very dim and both the very bright areas without saturating. And then if, for example, your sample changes intensities a lot over time or over Z, so basically whenever you have a data set where you have very bright and very dim areas, definitely you want to have a high bit depth. So why would anyone want to use a low bit depth ever in that case? Well, sometimes scientific questions do not require the fine intensity details, and therefore it is, or you don't have fine intensity details in your sample, and therefore you don't need so many bits levels, grade levels. And then sometimes the sample is very dim everywhere, and so there is no risk to saturate the detector, which is one of the reasons why you want to use a high bit depth. So then you don't have the need for this. And the advantage of using a low bit depth is that the imaging goes faster. So whenever you want to go fast, 8-bit is definitely better. You also save space because the 8-bit images take half the space on your hard drive compared to all the other bit depths. And the 8-bit images are much easier to analyze, so they demand a lot less computing power because they are less, like they are smaller. And also they can be used directly in normal software, like for example, you can insert them directly into a PowerPoint presentation, whereas the high bit depths need to be converted to an 8-bit first. But we have seen this together. It's not very difficult. So when you take a screenshot of an image that you have displayed on your screen, that is automatically an 8-bit image. So it is possible to change the bit depth post-acquisition in Fiji, and this is the way to do it. You go to image type and 16-bit. But you should only change the bit depth on a copy of the original image. Always keep the original image intact. And the bit depth of the image can be downsized to 8 bits, but there's absolutely no reason to upsize it because you are not going to generate more data. You're just making the file bigger. So don't go up, but you may go down, for example, to be able to insert these images somewhere else in the presentation. And then if you, exactly, so changing from a low bit depth to a high bit depth is never useful as the fine details were not acquired altogether. So you're not creating anything there. So what does if we look at the specification sheet of a camera, and this is one of the things that you have to do now because you have to collect information about your detector. So this is, for example, for the kinetics from photometrics. This is what the data sheet would look like, and then we're going to see how to read this. So we have different modes, basically, for kinetics. And in here we can see the dark current. So I don't know if you remember, but I've shown you where the noise comes from. And one of the things that I said is that the dark current creates a very low level of noise, but one of the things is that we cannot change it in the settings, so we say we ignore it. And we said the noise mostly comes from shot noise from light. But dark current, this is the specification, this is basically the minimum number of electrons that the sensor is going to detect. So even if you have no light, it will detect this. So this is the bottom of each image, basically, even if without light. And then we have the full well capacity, and I spoke about this well idea that we fill up a well with water. This is a full well. So this is how much drops of water we can get, how many electrons we can get at the maximum. And you can see that it changes depending on the settings that we choose. So if we use a high bit depth, we're going to have access to the full well, and therefore to the maximum dynamic range, and therefore we will be very unlikely to saturate. Whereas if we go very fast and we choose a low bit depth, we're going to have only 200 electrons, and therefore we will saturate very easily. But we go much faster. So you can see at 16-bit and 12-bit, we only go with this camera 88 frames per second. So frames is, it's often said frames per second, I mean images, how many images per second we can acquire. 88, and this is at the full frame. And if we want to go very fast, we choose 8 bits, and then we have almost 500 images, full frame images per second. And when we say full frame, this is 3,200 by 3,200. So people who work on a confocal will fully appreciate that if they do one image at 3,200 by 3,200, it's going to take many seconds. And now we're talking about 500 such images per second. And then we spoke about the read noise. So the noise is mostly comes, like very little comes from the dark current. Most of it comes from the shot noise that comes from light. But also we have the read noise, and so this read noise, you can see here that it also produces a few electrons. So this is the noise level, and it also changes quite a lot depending on the bit depth that you have. And so these are the different bit depths. And so we can see here that we have different settings. One of them is we're going to choose 16-bit if in our sample or over time we expect to have very dim and very bright areas. This is what we want, but we have to sacrifice the speed. And then we're going to have the full dynamic range of the detector. but only a medium speed and only a medium readout noise. If we want to go super fast, then we're going to choose 8 bits, and we will have a super high speed, but we have a very low dynamic range. It's very likely that we will saturate, or it's very possible that we saturate, and we have a much higher noise. And finally, there's also another setting that is a compromise, and it's sort of in between for everything. So you have this choice when you acquire on a detector based microscope or on a camera. You always have the choice between different bit depths. In general, on a point confocal, you're going to choose a low bit depth, and that's because there's no accumulation of the electrons. And you will use the high bit depths only if you are in a situation where you have very dim to very bright sample. If you realize that your images are often saturated and it's difficult for you to find the settings that allow you to show the bright areas and the dim areas, you definitely want to change the bit depth to a high bit depth. And so this is on the point confocal, and on the camera-based system, you often have at least 2 different bit depths to choose from, because on a camera-based confocal, we can go on a camera-based system, we can go super fast as well, and so we have to make these type of choices. Yeah. So I hope that in the future you will understand which case applies to you best and pick the correct settings. So now let's see how to detect saturation and underexposure, and we have different tools in our hands, and they're called lookup tables and histograms. So let's see that again. So most sensors acquire images in black and white. And we have then some tools to help us see the image, and they're called lookup tables. So it's a very strange name, but anyway, it's often abbreviated LUT or LUT. So what are the different lookup tables that are available for us? For example, we can have artificial colors. So this one is color coded in green. The image is normally black and white, right? It can be changing the brightness and contrast. It's also a lookup table. The intensity in the Z color coding or time coding as well. So where you apply a rainbow color depending on how bright it is, for example, or how deep it is in the sample, etc. All these things are lookup tables or LUTs. It changes the way the computer displays the data, but the data itself is not modified. So it's very safe to change that, but it can trick you. So you have to be a little bit careful with that. So the saturation and underexposure LUT is available in all microscopy software, because saturation and underexposure are artifacts. And so all software manufacturers, they will have something like this. So in the Nikon software, it's in here, and you will need to tell me where to find this in your software. So you'll need to do a screenshot like this where you can show me. And this is what it looks like. And so what it does is that it displays the colors in black and white, if ever you didn't have them in black and white. And then it adds this color mask where the saturated pixels, the ones that are the highest intensity level of the bit depth, are color-coded often in red, but it's not always the case. And those that are have an intensity 0, they are underexposed and they're color-coded in blue. So in the Zen software, in some software, you need to first reset the brightness and contrast, so showing all the bit depths available in the image to detect saturation and underexposure. So this is the case in Zen and in Fiji. Whereas in Zen, it's called the range indicator. In other software, you don't need to do that. So it's just a choice of the manufacturer. So it's called the range indicator in Zen, and then in Fiji, it is called high-low. So if you go there to Fiji, lookup tables, you have your image, you can apply the high-low lookup tables, and then this is what it will look like. And now this image is not acquired in a proper way because we have lots of blue in the background. And in Leica, it's called LUT. And I don't know in Olympus. So if someone has an Olympus microscope, please let me know. So when shall I check for underexposure and saturation? Well, just leave the mask on all the time. Always have this mask on, because this is an artifact. And again, your images are likely to be rejected And at the worst thing that can happen is that your data is wrong. So leave this on, okay? Oh, but I cannot see the color, the channel color. Yeah, it doesn't matter. This color is anyway artificial. The images are acquired mostly in black and white, except if you have a color camera. And it's not good to look anyway in color because we have the color bias where green always looks brighter than the others. So you're going to artificially push the blue and the red simply because you do not see it very well. So just remove the color bias and put everything in black and white. The color is anyway encoded in the image. So when you do the overlay, you will get these things in color. So all this blue and red in my images, I cannot see my signal. It's very boring. Well, good. That's the idea. If it bothers you, do something about it and change the acquisition parameters. If the image is correctly acquired, you should not see any red or any blue in the image. Okay, so change the settings and then it will not bother you again. So now if we look at, so that was the lookup tables. And if we look at the histogram here, this is also available in all microscopy software. You can see here on the x-axis all the possible intensities in this image. So from 0 to the maximum of the bit depth. And here you see the number of pixels across the image that have this intensity. So here we see this is a 12-bit image, and so there are 4096 levels of gray from 0 all the way to 4095. And if we look at the pixels that are at 0, we can see here there is a line of blue and red, right spot on the 0. So if we look at the intensity of the 0, we can see that we have many pixels that in the blue channel and many pixels in the red channel that are underexposed, and they have this 0 intensity, whereas the green channel is not underexposed. And if we look on the other side, we can see the opposite. So the green channel has many pixels that are overexposed, but the blue and the red channel are okay. So not good, we have saturation and underexposure in this image. And all what you can see here is that most of the photons that we have are really very much in the lower range. So this is the reason why the red and blue images were looking so dim, because most of the pixels there have a very low intensity. So it's not a very good, well-acquired image, that one. So it is much better to try and fill the histogram. It means try to stretch, let's say, the data all the way to the middle of the range, but without having saturation. And we always have a few spots that are saturated, so we don't want that, so we eliminate them that way. We try to fill the histogram, okay? It's okay to have a few saturated spots as long as it's not in your area of interest. So we try to use the full dynamic range. And we are going to talk about the typical workflow of how to set a single point confocal and the camera later today. And so we can change the settings to adjust this image. And when we do that, this is the type of image that we can get. And now we have no more saturation. So we can see we have 0 pixels that have 0 intensity in any of the image, and we have 0 at the maximum bit depth, and therefore these images are well exposed, and this is the type of histogram that we're getting. So this is what we're aiming at. So there should be no saturation at all, no underexposure at all in the areas of interest. And again, if you have a blob of antibody here and it's very bright and saturated, it's okay. When you publish this image, you can always say, there is a precipitate of antibody that is saturated in the corner. We ignored it in the image analysis. That's totally okay. So the bit depth, just want to mention that the bit depth is not the maximum intensity in the image. It's the maximum possible intensity in the image. Okay. If the image is not saturated, there is no pixel at the maximum bit depth. So when we look at the histogram is Fiji, so we have these 3 images here, and then if we go to analyze and histogram, then you will get this histogram, 1 per channel, and you will see in here the minimum and the maximum intensity in the image. Yeah, but we're going to have a little break now for 10 minutes, and I'm having a look at my my schedule. Yes.